Hey there, now that we know a variety of different factoring techniques, we can actually apply those factoring techniques and actually solve equations by factoring. When we set our expressions equal to zero, they now become equations. Specifically, we're talking about quadratic equations. Quadratic equations in the standard form are where we've been working with ax squared plus bx plus c, and once we set that equal to zero, it now becomes a quadratic. We're going to solve using the zero factor property, stating that if I have two factors that are set equal to zero, then one of those factors must be zero in order for it to equal zero. So here are our steps for solving. We're first going to make sure the equation is set equal to zero. Then we will factor, if possible, the quadratic expression that equals zero. We'll set each factor containing a variable equal to zero. Solve the resulting equations to find each particular root. Let's solve the equation by factoring. X squared plus 4x plus 3 equals 0. I do not see, first of all, it's set equal to 0, so we're good there. I do not see that there is a GCF. I have three terms, so I need to factor using our table. I need to find two numbers that multiply to 3 and add to 4. I see they are 3 times 1, so 3 and 1 are our magic numbers. Because there is no number in front of x squared, I can jump to the factored form of x plus 3 and x plus 1. And this is set equal to 0. Now for the new part. Then we'll set each factored piece equal to 0, giving me x plus 3 equals 0 and x plus 1 equals 0. And now I have like two mini problems that I can get x by itself. I'll subtract 3 on the left to get x by itself, and I'll subtract 1 on the right to get x by itself, giving me my two solutions of -3 and -1. These are what we call roots. If I were to graph this equation, I would find that my graph crosses the x-axis at -3 and -1. That is the objective in which we're following here. Finding out where our graph crosses the x-axis. What are the x-intercepts? X-intercepts, solutions, and roots and zeros, they are all the same language to mean the same thing. Let's try 8 minus 2x minus x squared equals to 0. Yes, this is set equal to 0, however, it's kind of in a weird order. So let's rewrite this in descending order, giving me negative x squared minus 2x plus 8 equal to 0. We haven't worked with anything where there's a negative in front of x squared, so let's factor out the greatest common factor of -1. When I divide everything by -1, we get x squared plus 2x minus 8 left over, all still equal to 0. I don't see now I have anything in front of x squared. 8 is not a perfect square number, so we're going to need to use our table to factor this trinomial. Finding two numbers which multiply to -8 and add to 2. 4 times -2 works, and 4 plus -2 works. So I'll rewrite this because there's nothing in front of x squared. I can jump to the factored form of x plus 4 and x minus 2, keeping that -1 in front from our GCF. Now we set each factored piece equal to 0. So -1 equals 0, x plus 4 equals 0, and x minus 2 equals 0. It looks like the one on the left is already solved. It has no x value. When I subtract 4 on the left and add 2 on the right, my options are -1 equals 0, x equals -4, and x equals 2. However, you're probably noticing we have a problem. -1 does not equal 0. So we can ignore that answer altogether because it's a false statement. Again, if I were to graph this, we see that our quadratic crosses the x-axis at -4 and +2. I've got x times 2x minus 5 equals 7. Sometimes we have to simplify before we can find the quadratic form, so we need to distribute to get rid of those parentheses, giving me 2x squared minus 5x equal to 7. We now have to set this equal to 0, so I'll subtract 7 from both sides to set it equal to 0. I do not see that we have a greatest common factor. I see I have 3 terms here, but that the first and the last term are not perfect squares, so I cannot use a perfect square trinomial. So we'll have to multiply using the AC method. So we'll have to find two numbers which multiply to 2 times -7, which is -14, and get add to the middle number of -5. -7 and 2 work. And now we rewrite our trinomial, splitting that middle term, giving us 2x squared minus 7x plus 2x minus 7 equals 0. We have to split our term because we have a number in front of x squared, and we have to take that into consideration when we're factoring. But now I have 4 terms. With 4 terms, we know we group them. So I'll group my first 2 terms and my second 2 terms together. I notice in my first 2 terms that they share an x. So when I divide my first 2 terms by x, I end up with 2x minus 7. I want to keep my 2x minus 7 in my second set of parentheses because I know they need to match. So I'm going to divide them by a positive 1 to keep everything the same. Now I see they have a common binomial of 2x minus 7 with x plus 1 left over. Now that it's factored, we'll set each factored piece equal to 0. So 2x minus 7 equals 0 and x plus 1 equals 0. Solving, I'll add 7 to both sides, and on the right I need to subtract 1. However, I notice on the left that x still isn't by itself. It needs to be divided by 2. So our two solutions are 7 halves and -1. Again, if I graph this, here I see -1, and if I were to take 7 divided by 2, we would get 3.5. So we see that's where they cross the x-axis. -5x cubed plus 35x squared plus 90x equals 0. It is set equal to 0, it is in descending order, and I do see that we have a greatest common factor of -5x. So I will divide everything by -5x. When we divide by -5x, I'm left with x squared minus 7x minus 18 equal to 0. So now we need to factor, if possible, that trinomial on the inside. I notice that 18 is not a perfect square, so we cannot use the perfect square trinomial. There is no number in front of x squared, so we're going to use the table. We need to identify what might multiply to -18 and add to -7. It appears that -9 and 2 will work. So again, because there's nothing in front of x squared, we can jump to the factored form with x minus 9 and x plus 2, along with the greatest common factor listed in the front of them. Now that everything is factored, we'll set each factored piece equal to 0. -5x equals 0, x minus 9 is 0, and x plus 2 is 0. And then solve each one. So on the left, I will divide everything by -5. So 0 divided by -5 is 0. I'll add 9 in the middle, so x equals 9, and then subtract 2. So notice that 0, 9, and -2 are all solutions because x can be 0. Solve by factoring. 121 minus 9x squared is equal to 0. I notice that there's not a GCF and that I have 2 terms. I also notice that 121 is the same thing as 11 squared, and I can rewrite 9x squared as 3x squared. And since we're subtraction in between, I can use the difference of perfect squares. So 121 minus 9x squared equals 0. Its factored form will be 11 plus 3x times 11 minus 3x using the difference of perfect squares rule. I can then set each factored piece equal to 0. So 11 plus 3x is 0 and 11 minus 3x is 0. I'll subtract 11 from both sides, and giving me 3x equals -11 and -3x equals -11. And then each side respectively will need to be divided by 3 and -3, giving me x is equal to a -11/3 and +11/3, because on the right here, I'll have -11 divided by -3, and a negative divided by negative gives us a positive. Graphing, I see that I certainly have -3 and 2/3 and +3 and 2/3 as the location at which my graph crosses the x-axis. The length of a rectangle is 3 more than twice the width. Determine the dimensions that will give a total area of 27 square meters. I'm going to first start off by drawing a rectangle, excuse me. We have no clue at what the width is. It gives us no hints, so we label that side as x. I then know that my length is 3 more than twice the width. So 3 more than twice whatever our width is will give me the length of our rectangle. We also know that area is equal to length times width. So putting it all together, our area is 27 is equal to our length times our width, so x times 2x plus 3. Now we can go about getting rid of our parentheses by multiplying x. So 27 is 2x squared plus 3x. We need to set this equal to 0 before we can factor, so I'll subtract 27 from both sides. Because I have a number in front of x squared and 2 and 27 are not perfect squares, I'll need to multiply 2 times negative 27 so that we find some things that multiply to negative 54 but yet add to 3. And 9 and negative 6 work. Because there's a number in front of x squared, we need to split our middle term to take into consideration that 2x squared. So I'll rewrite this as 2x squared plus 9x minus 6x minus 27 equals 0. We have 4 terms, which we know we need to factor by grouping, so I'll group my first 2 and my last 2 together. The first 2 I see share an x in common. When I divide them by x, I'm left with 2x plus 9. I see my second set are divisible by negative 3, and when I divide them by negative 3, I get 2x plus 9. I see now we have a common binomial of 2x plus 9 with the leftovers of x minus 3. Now that it's factored and set equal to 0, we'll set each factored piece equal to 0. When I solve, I end up with x equal to negative 9 halves and x equal to 3. Let's stop a moment and think about length and width. Is it possible to have negative 9 half meters? Probably not. So that answer, although a good answer, doesn't make sense in the context of the question. So we've narrowed it down to our only option being x equals 3. Well, then we can find out what our length and our width are by substituting 3 in for our x values. So if I substitute 3 in for x for our length, I have 2 times 3, which is 6, plus 3, which is 9. And then on the left for our width, x is equal to 3. So the dimensions of our rectangle are 3 meters by 9 meters.